Okay, physical science time. We're gonna, as I said a second ago, get crack-a-lackin'. My mic has fallen down. Yeah, that's more professional. It was too revealing. Okay, the first thing I want to ask you is for you to define ionic and covalent bonds, as your bell work had asked you to do. So I'll let you volunteer. If someone could raise their hand to describe an ionic bond, I would appreciate that. Let's hear it, Jose.
Ionic bonding is the force of attraction between the opposite charges of ions in an ionic compound.
Mm-hmm. So, first of all, what we should gain from that is that it's a force of attraction. So we're talking about bonding. And one thing we're going to put is that it is a force. Let's underline that. Of attraction. It's a force. Okay, we'll come back to that. Remember what Josie said, which I don't know that the video picked up. In fact, I'm pretty sure it didn't. And so if you didn't hear, what Josie said is that it is a force of attraction that bonds together two ions, two differently charged ions. Who would like to tell me what covalent bonding means from your weeks and weeks of reading? Cody, yes?
The attraction that forms between atoms when they share electrons.
Mm-hmm. So again, it's a force of attraction, but in the case of covalent bonding, they, instead of it being the force of attraction between differently charged ions, it is the force of attraction between atoms when they share. Did you say what the noun was, Cody, when they share what? Or what did you say? I should have just asked that. When they share electrons. Yeah, exactly right. Let's also at this time write down the objective, which is define and balance Oop, that is not it. That's for 21. Does anyone have it on their, maybe on their lab? Do you have your lab pulled up, Miranda? What was it for chapter 20? Oh, because you didn't get one, because I was gone for that whole month. So let me think of what it would have been. Well, let's just very simply put, describe bonding and name bonded chemicals. Chemicals, I guess. I don't like using the word chemicals as a noun because it sounds kind of, you'll forgive me if I say Facebook mommy, where Facebook mom is always putting on there, don't drink Crawford water, it's got chemicals, or don't eat Cheez-Its, they're made of chemicals. And for one thing, maybe we should write this down. What is chemicals? What around you is made of chemicals? You could talk about like Takis. I'm sure there are chemicals in Takis or all the other stuff your mom doesn't want you to eat, or soap. But what is chemicals? What around you is chemicals? What? Markers. What else? That's it. Just Takis and Cheez-Its and markers.
This table.
That table, okay. His computer, that backpack. What? Cody's phone. Cody himself. Cody himself. Maybe not, depending on your philosophy or your religion, the part of him that makes him Cody. But everything, I'm going to put a star next to that. Everything is chemicals. If I had another sticker on my board, I would probably go crazy because it's getting to be like mostly stickers and less board. But I would love to have a sticker that says everything is chemicals, just to really stab it in the guts of Facebook moms, because everything is chemicals. So you can't, that really doesn't, I know what they mean. They mean like harmful chemicals in the same way that when I say we have to use goggles in the lab and we're working with harmful chemicals, it is true that some chemicals can be damaging to human health. But the word chemicals has kind of like a bad rap. Like even your boy has, you could quote me as sometimes saying that one of these Keurig pods has a chemical taste. And I should know better because everything that comes out of the Keurig is chemicals. But you know what I mean if I say that. It has like a kind of, I don't know, like an artificial or poisonous. And that's the way that the Facebook mom means it too. But everything, and you're being a technical, pedantic person when you're using this, but everything is chemicals. What's the little asterisk? Except what? What in the universe is the only thing that isn't chemicals? Okay, well, again with the nothing. The void of space, sure. What else? What else? We talked about this the last time we met in the video discussion too, but that was like a month and a half ago, so I'll forgive you if you don't remember. What else? There's one other thing that the universe is made of. There's chemicals, which I'm getting at is matter. They're kind of synonymous. Chemicals are like the building blocks of matter. There's the vacuum of space, thank you, Lucas. And what else? What else is in the universe? Which is a type of? No. We've been talking about this all year long, too.
Light.
Which is a type of?
Wave.
Which is a type of? Let's do hangman. Come on. No, there's no A. No, there's no I. There's no B. Energy. Thank you. Energy. There we go. Thank you for reading your book, Miranda. So everything, as we said last time, in the universe, once again, last time was a month and a half ago, so I am currently in the process of forgiving you. But everything in the universe is either energy or matter, and a way that we describe matter is its chemical composition, what it's made of, what the building blocks of it are. So chemicals are the building blocks of matter. But everything is chemicals. Everything is chemicals, and we're going to today describe bonding and name bonded chemicals. So our main thing that we're doing is this naming bit. We're going to name them. The converse of that is that we're also going to be, once we're given the name, we will tell what the formula is. So we're alternating between names and formulas for chemical elements, chemical species. So bonding is a force of attraction. What's important about that we use this word force here? Do you remember from the very beginning of the year what a force is? Thank you, Tommy. A push or pull on an object. What are the objects in question here? What are the objects in question? Okay. Chemicals, atoms, yeah. Chemicals, atoms, ions. We want to be very careful that technically the word atom, which we will use a lot, technically an atom has a neutral charge. We talked about this in the last video too. Technically an atom, maybe it was a video before that, but technically an atom has a neutral charge, so we want to be kind of careful that when we're talking about charged particles, we correctly call them ions, and you'll remember that from the last chapter too. So charged particles are ions, uncharged particles of that kind are atoms, and we're talking generally about chemicals. Here are these very, 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 very small things. And this force of attraction is a push or pull that generally is pulling them together. Well, that's what attraction means, is when they're pulled together. Have you ever been attracted to someone? This is a fun question for freshmen. Of course you have. The only person, surprisingly, that nods is Peyton, and I know I know what it's like to be a freshman. But what is the force of attraction there? God bless you. What does it mean to be attracted? What does that word mean? Yeah, pulled towards. If you are, as a freshman, and as freshmen often are, attracted to another person, being, yes, that's very inclusive. If you're attracted to another being, you feel a pull towards that that thing. So you know what that feels like in your heart, probably, unless you're some kind of psychopath. But that same, that's a metaphor, of course, but there's a similar thing going on with atoms where the attraction pulls them together. So let's describe that in ionic bonding, first of all. Now, ionic bonding happens when ions form. Ions form from atoms in order to achieve stability. That's our first postulate of ionic bonding. Ions form from atoms in order to achieve stability. Let me give you an example. I'm going to erase all this later when we go on to covalent, so it's okay if I infringe upon its territory. I'm looking at our periodic table. Do you see my friend sodium here? And you know, because you know the cheat code to do this, looking at the periodic table, how many valence electrons does sodium have? 1. How many total electrons does sodium have? 11, but it has 1 valence electron, 1 electron in its outermost shell. And let me tell you, here I'm going to make another little side note over here. Valence electrons, those outermost electrons, valence electrons are the ones, I was going to say used, but I don't really like that. Now, okay, mic'd up again. Who knows how much we missed there, but that's okay. We'll just keep going. Everything that's on here is still on the board. It does have 2 valence electrons. You're correct about that. How many does fluorine still have? 1, 2, 3, 4, 5, 6, 7. Now check it out. How many electrons will the fluorine gain? How many can it gain? 1. It can only gain 1. So something. This isn't going to work, is it? What has to happen? There has to be another one. There has to be another fluorine. So now there's another place for that valence electron to go. So unlike NaF, which is sodium fluoride, it's not just SRF, it's SRF what? We don't say it like that. SRF2. Yep. Which we still call strontium. What's its last name? What's his surname? Fluoride. Yep. We changed the ending to "ide" with these. The analogy I was using on Friday is that strontium's got 2 ice cream cones, and he wants to give them. He doesn't want any, and so 2 fluorines come along, but each of them only wants 1. So how many is he has to give them each one? Okay. Another example. Does everyone have this one written down? Can I erase this? I'm gonna. Let's do. What if we had potassium and oxygen? How many for potassium? 1. Oxygen?
6.
1, 2, 3, 4, 5, 6. Uh-oh. This potassium really left the oxygen hanging. What has to now happen? Wait, there has to be another potassium. Basically, it takes twice as much potassium as oxygen to form this compound. This is going to be what? Tell me its formula. K2O. Yep. And what do we name him? Yep, potassium oxide. Very good. Let's complicate it a little bit more now. We'll do one more of even more complexity. Can I erase it? You guys are writing these really fast, or else you're not writing them at all, and I hope it's the former. Can I erase this?
No.
Thank you. Turn to page 619 while you're waiting. Is that the right? Am I right? Yep. 619. On page 619, what's special about 619, Josie, that we talked about on Friday? It's a chart. But yeah, it's a chart of polyatomic ions. Now? Okay. There is a chart of polyatomic ions. Poly meaning what? I'm just going to write this word down real quick. Yep, polyatomic ions. Poly meaning many. Atomic referring to atoms. And they're ions. They're ions made of, instead of one atom, like the ones we've done so far, they're made of many atoms. And there's a list there. They have set formulas, and each formula has a set charge. And so instead of having an electron dot diagram, let's just call this one, let's call this sulfate, SO4. And what's its charge?
-2.
Yeah, 2 minus. How did she know that? She just guessed?
It's in the chart.
It's on the chart. So SO4 has a charge of 2 minus. Let's say we're going to bond it with sodium. How many valence electrons does sodium have? 1. Is that going to work? Will 1 sodium make this sulfate stable? No. We need 2 sodiums, and so what's its formula going to be? No, it's Na2SO4. We no longer write the charge because the charge has been neutralized by the sodiums. And we name this what? Sodium sulfate. Has a polyatomic ion in it. Now let's do the exact same thing, except instead of sodium sulfate, let's have calcium sulfate. Well, in my diagram, instead of drawing sodiums, now I'm going to draw what? Calcium, which has how many valence electrons? Calcium has 2 valence electrons. So check it out. What's my formula for calcium sulfate? CaSO4. No 2 needed, right? Because the calcium already has a 2+ charge. Is this a little bit better, Lucas?
Yeah, it's better than that.
I don't know what you're talking about, but on Friday, Lucas told me, you're a bad teacher. I wish someone would teach me this right. So the charges have to match. That's basically it. The charges have to match. The charges, we say, have to add up to 0. When I say match, one's positive, one's negative, they have to add up to 0, which means they have to be the same number but added up to 0. That's ionic bonding. We'll do more practice with the naming, but that is ionic bonding. Questions about any of the steps, I guess, things, proponents, I don't know what you call this, positions? Questions about the suppositions of ionic bonding. This list I have here. Does anyone still need that? I will erase it otherwise. Is anyone still using the diagrams over there? Let me ask it again.
No.
Okay. Now we're going to move on to talk about covalent bonding. What do you think is the first thing I'm going to do with covalent bonding? What's the first thing we do whenever we have any? Yeah, we'll break down the word covalent. Co meaning what? If you,
Together.
yeah, co meaning together, and valent meaning referring to what?
Electron.
Yeah, referring to valence electrons. So they're valence electrons that are together between two atoms. Whereas, let me write this word down. I love this word, whereas. Whereas ionic bonding happened between a metal, which is the cation, and a nonmetal, which was the anion. Covalent happens generally between what?
Two metals.
No, try again.
Two non-metals.
Nonmetals. What kind of bonding happens between two or more metals? BT dub, Lucas.
They form a new metal.
Two or more metals, we call that metallic bonding. That's kind of another little side note. I mean, that is a vocab word and it is on the test, but it's called metallic bonding. But we're focusing mostly on ionic and covalent. We've already talked about ionic. So covalent is generally between two or more nonmetals. And whereas ionic bonding, I'm going to try to spell my favorite word. Whereas ionic bonding, try to spell even this other word, bonding dealt with giving and taking, I guess, transfer, let's put that, transfer of electrons. Covalent involves what? What are they doing in this one? It's not transferring. One is not getting and the other one's receiving, or giving and the other one's receiving. They're doing what? Sharing. Just like when you was in preschool. Sharing. So let's diagram that. Let's say we have two nonmetals. Let's say they're oxygens. 1, 2, 3, 4, 5, 6. Why would I draw 6 dots around Mr. Oxygen here? Because it has 6 valence electrons. Let's say we have another oxygen. 1, 2, 3, 4, 5, 6. So we know that when a metal is around, the metal will give its electrons and the nonmetal will take its electrons. And then they'll be bound together by electromagnetism. But in this situation, when they're both nonmetals, neither of these particularly wants the electrons. They both want 8, remember? Want. Atoms don't think. But they are both more stable with 8. So what can they do? What can these two do? I said they can share. So instead of being these two separate things, it becomes this. They share a total of 4 valence electrons. And now each of them is as if it has, look, how many does this one have? 1, 2, 3, 4, 5, 6, 7, 8. And this one, there's an overlap here. 1, 2, 3, 4, 5, 6, 7, 8. They're both more stable. This was O. This was O. What's this? O2. What's O2? The oxygen that we breathe is O2, right? And it's because it has shared it in this way. Sharing. The last word is sharing. They share. They are covalent. They share valence electrons. So what's holding them together? Well, the electrons that they're sharing are attracted to both nuclei. So it's still the electromagnetic force. They're not attracted to each other, but they're attracted to each other's electrons. So how do we name this? Well, in order to name it, let's do a different one real quick, and then we'll be done. Let's say we have carbon and 2 oxygens. Well, each oxygen has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And the carbon has 4. 1, 2, 3, 4. Let me draw it a little bit smarter. I think this actually isn't the right way. Let me do it like this. There we go. This is going to look really nice. And it's actually going to be correct. Okay, so check that out. What are those dots? Valence electrons. How many does the carbon have?
4.
No, it starts with 4, but once they've bonded, it has how many? 8. How many does the oxygen have, this oxygen? It starts with 6, but now it has 8. And then this one, 8. They're all happier when they've bonded, right? What's the formula for this little guy? CO2. You already know what his name is. What's CO2? Carbon dioxide. What page is my other chart on, Josie? 621 has a list of Greek prefixes for covalent bonding. And that's all we do for naming covalent, is we tell how many there are with the Greek prefix. So carbon dioxide means 1 carbon and 2 oxygens. Potassium, no, that doesn't work. Phosphorus pentoxide means 1 phosphorus and 5 oxygens, because penta means 5. So for covalent naming, we just go between that chart and how many there are. So the charts you need from your chapter are 619 and 621. You'll have those charts also on your test. Questions about covalent bonding, where they share. Questions? What's holding them together? What force of the universe? Still electromagnetism. Questions about ionic bonding? Questions about our tiny little sentence here about metallic bonding? I don't know what I'm going to do about the sound in this video, but